Welcome to the second part of our lecture about heat gain and heat loss. Specifically, we'll be talking about insulation. As you remember, possibly from the last set of slides, insulation's purpose is to control heat gain and heat loss in the building envelope, and it primarily prevents conductive heat loss. It's placed within the framing, between wall studs, in between floor joists, and in between ceiling joists or the bottom cord of trusses in the roof structure. Although we have a whole class about residential codes, building codes, and zoning, as well as a commercial set for those of you who might be building inspection or doing the base degree of architecture, it is important to keep in mind that there are minimum requirements that we have set in the building code, and we will be referring to that in this class as well. These, again, are the minimum requirements. We can always go above, and because we're going to be talking about sustainability, we are going to refer to additional steps that could be made to get above these code minimums. In this lecture, I'm going to go over the different types of insulation, both their materials and their form. There are much more specific data available in your reading, such as R-value, ranges, relative costs, installation, etc., done in more of a bullet point form. So when you're doing your homework and when you're doing your term project, please refer to the book for that. I'm going to talk a little more globally about these types of insulation and the materials that are used to make them. And we're going to start with fiberglass. So fiberglass is mostly in two forms: batt, which we see here, and blown-in insulation. By far the most common type of insulation is batt insulation, and the most common type of insulation of any material is fiberglass. It's made by melting glass and spinning the molten liquid to produce thin fibers, much the way cotton candy is made, but at a much higher temperature. All fiberglass insulation produced in the United States today contains at least 30% recycled glass. The most common source of that recycled content is glass culled from window glass manufacturing. The rest is recycled beverage containers. A binder is added to fiberglass to hold the fibers together. The most common binder is phenyl formaldehyde, which might result in low levels of formaldehyde emissions over time, though most of the formaldehyde is removed during the baking process. One fiberglass insulation manufacturer, Johns Manville, has switched entirely to an acrylic binder to eliminate the formaldehyde off-gassing. So as we talk about wood, that off-gassing becomes more of an issue, and when we talk about ventilation and air, indoor air quality, formaldehyde is something that occurs naturally in nature, but in large amounts it is not good for us to breathe. It's actually used in embalming bodies. So large amounts is not good. Small amounts are acceptable, and so that's why Johns Manville has gotten away from it. There's also been some concern that glass fibers might be carcinogenic, like asbestos is, but worry about this has decreased in recent years following new studies. If fiberglass insulation is properly installed so that the insulated cavity is separated from the living area by an air barrier. You shouldn't be too worried about fiber shedding once the installation is complete, but it is important to wear gloves, goggles, and a dust mask when installing or removing fiberglass. Also handle the bats carefully to minimize dust generation. The other thing I might mention about bat insulation is it's not clear from these images, but bat insulation can either be just the material, whether it's fiberglass or cellulose or some other material that's making the bat, but a lot of times the exterior of it will have a craft paper backing on it. Craft paper is a brown paper bag look, and some insulation, bat insulation, will also have a foil layer that will help radiate heat either back into a house or outside the house, depending on the climate. The next one is cellulose, either bat or blown. The book talks about it at some great length. Cellulose is the structure that is in part of the protein structure that is in grasses, bamboo, wood, it's cotton. So any of these items can form cellulose insulation. Recycled newspapers are a very common way of creating the blown especially. And the image that we see on the left is actually recycled blue jeans that have become a bat insulation. This type of insulation is becoming more common in residential buildings. It's certainly used quite often in attic spaces, as we see in the image to the right, and in renovation work where installing a blown-in is a lot less difficult to do in an existing building where there's already siding and drywall than putting bat insulation in. The other thing I would mention is, again, one should be wearing a dust mask whenever dealing with especially blown-in insulation, but in general, because it is a paper cotton type of product, it is not as dangerous to our skin. However, there can be flame retardants that are added in, which could have health and environmental concerns. So if a person wanted to wear protection, there's nothing wrong with that. But fiberglass is more dangerous to install than cellulose would be. The next type is mineral wool, and mineral wool typically comes in rolls of bat, like we see towards the right, but it can also come in boards, which we see to the left. So boards that are specifically sized to fit in between studs. In this case, these are metal studs that we see there. Mineral wool is very similar to fiberglass, but the raw material is rock, literally rocks, and often basalt, which is a volcanic type of rock, or it could be slag. And I will say that in my own house, I had some rock wool in the walls of a garage that had been converted at some point in the late 60s, and the mineral wool was black, which basalt is black. The slag, if it is made from slag, is a waste material produced mostly from iron ore smelting. So if mineral wool is made from slag, that is a pre-consumer recycled product, similar to fly ash, which we saw with concrete. As with fiberglass, often a phenyl formaldehyde binder is typically used in the manufacture. Mineral wool bats are a higher density than fiberglass bats, and they block sound more effectively. They're more fire resistant, and that is especially important in commercial buildings where there are more fire separation requirements than there are in single-family residential. However, it is important to keep in mind that the material is twice as expensive as fiberglass or cellulose, which is why we don't see it as often. I'd like you to note also the fact that the truss forms a fairly tight corner at the heels, which is the bottom corners, and then the top chord is extending a little bit to form a rafter tail, because our next slide is going to show a better way of creating that edge condition. I'm going to jump to the bottom where it says use a raised heel truss, because this image is showing exactly what we want. It's really important with bat and loose fill to not squish the insulation. When you squish the insulation, so you shove it into a space in order to get it to fill a gap, you actually lose some of the R value. And that is what we describe as the difference between an R value and an effective R value. The design R value is when it's installed properly, and the effective R value can be lessened if it's not installed correctly. And usually, as I mentioned, it's because it's been smushed, and the less air that's in there, the lower the R value. This is especially important for fiberglass, bat and blown in and loose fill cellulose and bat cellulose. Using a raised heel truss is the best way to deal with this. So we see this image to the left. We have the full depth of insulation that's going all the way to our outside edge. We're not seeing insulation in the exterior wall below the bottom of that heel, but know that that would be filled as well. And we also see the arrow indicating air movement with a little piece of a darker brown that is at the bottom of the top of that arrow, which is a baffle. It's a shorter baffle, but again, we want to install a baffle in there so that insulation isn't spilling out into the, it's a boxed eave in this case that we're seeing. And we've got a continuous soffit vent, and that's allowing air to come up and move across. Your book talks about it, but just to remind you, the reason we want that air movement is whenever we have air moving through a space, it's going to help keep moisture from collecting in the envelope in an unhealthy way. The dew point is where water vapor turns into liquid water, and because outside of the insulation envelope, the building envelope, we are going to have a lower temperature, and we don't want that water vapor to turn into liquid water where it can sit. It can cause mold to grow in our insulation or cause problems with our wood. So that airflow in our attic space and under our houses, also in the crawl space, is very important. Just to add a couple more notes, the other thing that can affect the effective R value of a wall assembly, a floor assembly, or a roof assembly is the framing factor. So we saw when we looked at advanced framing that when we have fewer thermal bridges, we have an effectively higher R value than we do if we have standard framing. Also, insulation loses its effectiveness when wet or if it freezes, which again goes back to that idea of making sure that we have air movement through. And unfortunately, it does lose its effectiveness as it ages. Especially loose fill tends to compact over time, and so it needs a top off, if you will, to add more inches to the overall